Is it you?
Hey, yeah, this is Daniel. I don't see my video though.
I don't see a video.
I'm trying, yeah. Hello, okay. Yeah,
I see it.
there I am. Hello.
Hello. Nice to meet you again.
Nice to meet you.
So, can you share your screen, this presentation?
Yes. Which option should I use? Because I don't see share here. I see demonstration. Okay, demonstration is sharing probably. Exit full screen. Yeah, share. Okay. Do you see now?
No.
Mm-hmm. Full screen. Share. How to grant access? Okay, sorry.
Yeah, probably it will ask you about some access to your.
Yes, open settings. Okay, I have to tell my computer that this software should have access. I see. Click here. Sound and camera. Oops. Yeah. Let me 1 second. Demonstration. I want to share this. Share. How to grant access. Yeah. Screen access. Yeah. Mac. On the yeah. Open settings. Yeah. Okay. Yeah, somehow I need to tell my computer to be connected to this platform you guys are using. It's all coming in Russian.
Yeah.
Yeah. Open. However, you can say this one restriction. When you create a joint meeting, select a browser. MacOS. Okay. Yeah, the problem is I don't screen access. Okay, let me see.
Do you use Firefox?
No, but I can open this in Firefox if you prefer. Yeah.
No. Oh, it depends on.
Hang on a second. I'm using Google Chrome.
I see.
The table of contents. Choose Apple Mail settings. Okay. I think it's giving me the instruction here. System preferences, security, and privacy. Okay. And now in the sidebar, screen recording. Yeah. Camera. Well, let me open this link in another in another browser. Let me use.
You can try another browser.
Yeah. Let me see. Okay. It's loading. Accept. Okay, now everything comes in Russian only. Hello. Okay, I think I'm installing the application in my laptop.
Oh,
Not sure that's gonna help, but let's try it.
application Yandex Telemost application, some kind of.
Yes, Yandex, yeah, that's the one. Yeah.
Well, actually, as far as I know, it's not necessary. Typically.
Yeah, but the problem is since it's not letting me go through the browser, join meeting. Okay, let me see if I click now on the link. Open Yandex, okay? Now I'm gonna put okay. Okay. I'm gonna put Dani Figueroa join meeting.
No. You have some second.
I had a second, yeah. And now share a screen. Now it's in English at least. You see open system preferences, Yandex. You see, now I find it, I think. Yandex, later. Share screen. Can you see my screen now?
Yes.
Finally? Okay, good.
You did it, yeah.
So, excellent. I'm happy I did it because I wasn't sure, you know.
I'm sorry that you ever had such problems.
Okay. So I'm gonna go full screen here. Let's do just play.
Danny, we're making this seminar in conference hall.
Yeah.
Give me a couple of minutes. I will ask. I will come with people. Okay.
Yeah. I'm here.
У нас не оказывается внутри эксперимент, я встретил коллегу, внутренний эксперимент, двойной распад, все загнулось участки. Все закрылось. Ну, я не знаю, как он назывался, честно говоря, я просто никогда не интересовалась, потому что я все время всегда интересовалась тем, что конкретно я делаю. Я просто встретила Сашу, мы с ним работали в кафедре общей физики, он сказал, что он теперь на Калининской АЭС работает, а это закончилось. Ну, потому что, говорит, он что-то ну, я просто спросить его в институте. Обычно скажу,
Сережа ушел, да? Он пошел делать. А тут какой-то были технические проблемы, которые решили создавать людей.
Да, они ну, один вообще ничего не
нет. Ну, вот уже есть.
Да.
Более того, на этот термин альпинские, ну, если смотреть, можно смотреть низко,
Говорит, не хватает.
такой жесткой конструкции, что вы берете,
Ну, попробуй, посмотрите,
его есть, да, и не прямо жестко.
да.
Там
Okay. People are coming.
Excellent. Yeah.
Okay, I think we can start our seminar. Today we are happy to welcome Daniel Figueroa from IFIC, Valencia, and he will tell us about the early universe, numerically speaking.
Mhm.
So please.
Thank you very much. Shall I start?
Yes.
Okay. Can you confirm you see the full screen?
Yes.
Okay, excellent. And is it okay I show it like this? Is this good enough? Or you prefer full screen? Maybe it's better full screen, right?
Full screen is better. Somehow.
Okay, excellent. Well, I'm going to start. Thank you very much for the invitation. It is really a pleasure to be virtually with you all. Somehow in this application, once I go to full screen, I don't see the video, so I don't see your faces, but I assume you are there because I hear some noises. So really, thanks for having me. This is not the first time I'm giving a seminar in INR. I actually gave one in 2014 when there was gay civility of there. And I remember it went for 2 hours. So my question, first of all, is do we have 1 hour limit here or we can go as long as we wish?
Well, you can spend hour and a half, I think. It will be
Okay, that sounds good. Okay. Thank you. So let me then really start. So essentially, that's right. I'm going to speak today about the early universe from a numerical point of view. Okay? Because the universe obviously is a very broad and generic thing, but I'm going to speak about numeric. So an alternative title of my talk could have been The Art of Simulating the Early Universe, because that's precisely what I'm going to try to show you, how to simulate with certain techniques the early universe. So let me set up my clock here so I don't go much over time. All right, I have it now in front of me. Let's begin. So the early universe, of course, in front of an audience like people at INR, I don't need to introduce. I mean just the very first second of the universe, including period of inflation, reheating, and thermal era before BBM. Okay, that's what I mean by early universe. Now, we speculate with the possibility of having, in this first second of the early universe, a bunch of phenomena, from quantum fluctuations to particle production to phase transition or cosmic defect, and maybe others. Okay? Just one comment, sorry guys. I hear a lot of noise. Is it possible to mute yourself first, and then you let me know when you have a question? I hear an echo myself.
We don't.
Sorry, we don't. Do you hear some noises from us?
I hear like echo of my own voice.
Your own voice.
My own voice. It's like very distorted sound, you know. Okay, now I don't hear you because you are muted, of course. Okay, shall I continue? I hope that is a yes, but I don't hear nothing now. Okay, you are completely mute. So, in the early universe, we speculate with a possibility of a bunch of phenomena. These phenomena are very interesting because even though they can be very different among themselves, they share, however, a common factor. And this common factor is that they are characterized by nonlinear field dynamics. At least the phenomena I'm highlighting here, they really have in common that they, at the end of the day, if you want to compute them in full detail, these are nonlinear phenomena, and you need to characterize these nonlinearities. And of course, these extend not only to these phenomena, but to their possible observational consequences, such as the production of gravitational waves, the realization of baryogenesis, magnetogenesis, or black hole formation, for instance. And these nonlinear aspects, of course, extend also to non-canonical scenarios, such as non-minimal gravitational interactions, non-minimal kinetic theories, or more advanced aspects of fluid dynamics, such as turbulence or thermalization. So if there is one message that I want to pass you, or one message you have to take home, is the following. From now on, there is a new guy in town. Its name is Cosmolatis, and Cosmolatis wants to become your friend, okay? So essentially, you can become friends with Cosmolatis by either reading our lattice review, because this is about lattice techniques that we use in this code in order to deal with nonlinearities, or if you are brave enough, you can jump into the code manual, which, by the way, both of these documents are actually over 100 pages, so, well, you need to be brave. Now, once you are brave and you get yourself introduced into how to use Cosmolaris, what Cosmolaris can do for you, it can simulate a scalar gauge field dynamics, nonlinear dynamics, with self-consistent expansion of the universe, which I will comment later on more what this is. It is written in C++ with a modular structure that separates physics from technical details. So if you are theoretical physicists who don't want to know much about the technicalities behind the code, you can still proceed to use it. Or if you are a geek of informatics or IT and you really like to go inside the tribes, well, I mean, you have your opportunity to go into the technicalities with Cosmolatis, but it's completely separated from the physics. It is parallelized in multiple spatial dimensions, which is a very important question, very important aspects, because it means you can run this code in clusters of computers, and you can even run it, say, with thousands of cores of processors at the same time, but you write everything like if it was in serial, as close as possible to the continuum, okay? It comes already with a family of algorithms with different accuracies from order time step squared to time step even to the 10th. And these are algorithms that are already pre-programmed in the code, so you just choose them from a menu in order to do your simulations. So if you want to know more information about Cosmolaris, please visit our website, cosmolaris.net, where you have all kind of information about what our code can do, about the updates, about how to download it, about how to use it, about news, etc. Okay, now let me be more specific. What kind of field theory the current version of Cosmolaris can deal with? So essentially, Cosmolaris can simulate the dynamics of any singlet scalar sector, no matter how many scalar fields you have. It can simulate the dynamics also of abelian Higgs sectors or U1 gauge sectors. Again, no matter how many of these charged scalars of gauge fields you want to add. And it can deal also with non-abelian interactions of the type SU2, like in the standard model, for instance. Again, you can use you can add doublets, no, for this, and then you can have the full structure of gauge interactions of these non-abelian interactions. And of course, you can do it for arbitrary interactive potentials of this scalar field. No matter how nonlinear or complicated these potentials are, you can simulate their dynamics. And it does simulate the dynamics of all these fields over expanding background. Now, the expansion of the universe, of course, can be dictated either through the Friedman equation. So you collect all the energy densities and pressure expressions from scalar and gauge fields, and you can sort the Friedman equations and solve them together with the field dynamics. Or if you want, you can put a fixed background. Okay, you can do either situation. Just to give you an example, so you get a taste of what I'm talking about here. Imagine you want to simulate the dynamics of a single scalar field. So this is the Klein-Gordon equation of this scalar field. It lives in expanding background, no? So there is friction term here. And typically we do this trick. We define a conjugate momentum, which is appropriate variable to determine the velocity of the field amplitude. And we write equations into two sets of first order differential equations. One is the kick that involves the conjugate momenta, another one is the drift that involves the amplitude of the field variables. So essentially, Cosmolaris is a code that puts your fields in a lattice. So you're going to have a set of regular points with lattice spacing, so regular distance between these points in 3 dimensions. You can do this in arbitrary dimensions, actually, Cosmolaris is prepared, and there will be a maximum length of your box. Now, you choose what is the number of points or dimensions, what is the length of your box, and what is the time step. And naturally, in your lattice, there's going to be always a minimum infrared momentum, okay, which is determined by the length of the box, or a maximum ultraviolet momentum, which is determined by the number of points per dimensions you have here. Or if you want, by the lattice spacing. What is your ultraviolet resolution? And of course, this was an example for gauge fields, for scalar fields. For gauge fields, then what you have to do is to introduce links and plaquettes pretty much as people do in lattice QCD. Except that here we don't do path integral. Here we do the evolution in time of the dynamics of the fields. In order to solve the equations, the computer doesn't know nothing about units. So essentially, you have to choose program variables, which in order to turn your variables dimensionless. So essentially, you have to choose three constants. Typically, alpha, it's a conformal redefinition of your time variable. And it just amounts to choose this coefficient here. A is the scale factor. Omega star is a typical frequency in your problem. So you have to choose what is this frequency, and then you make dimensionless space-time units. And then you have to choose a typical field amplitude, and you make dimensionless field amplitudes like this, okay? And then the gauge fields, you normally normalize them with the frequency. So here is an example. Imagine you have a situation in the early universe where you have an oscillatory scalar field with an initial amplitude and a typical period. This period changes in time, but let's say initially it's fixed to a given specific number, no, in whatever units. And then this scalar field oscillates and is damped due to the expansion of the universe. So a good choice of your variables.
Dennis,
Yes.
question.
Can I ask a question? Eta is not a conformal time, right? It's kind of alpha is not 1.
That's correct. I call this the alpha time, which means if alpha is 0, this is ordinary cosmic time. If alpha is 1, it's conformal time. If alpha is something else, it's alpha time. Okay? And for every problem, you can choose your value more conveniently.
So it is more convenient sometimes not to solve questions in conformal time.
Absolutely. This depends on your potential of your interactions. That's right. Yeah.
Okay, thanks.
Yeah, this is correct. And here, thanks for the question. And here is an example. In this example, the oscillations of the period of my oscillatory guy are not constant. So the most clever thing is to choose appropriate alpha such that the period in the new eta tilde variables becomes constant. You see? So this really depends on your interactive potential. So you have to, for every case, you have to make a clever choice. All right? That's the idea. But that's really the idea, that you have the freedom to choose it. So here you see F star, I choose the initial amplitude of my oscillatory field, omega star, the initial period, assuming it's not going to change much. And then alpha, if you choose it clever enough, you can make the period constant in this alpha time variable. That's the idea. Then, of course, you have to normalize your potential into program units, which means to turn it dimensionless, but this is as simple as normalize it by the choice of F star square. Remember, F star is what normalizes your scalars, and omega star square. Remember, is what it normalizes your space-time variables. Then, you specify your potential of interactions, you take first and second derivatives, and you are done. Essentially, for any scalar gauge theory, you are done. You can essentially introduce into a file your parameters, and then you run your code. Once you've compiled it once, if you want to change your parameters, you don't need to recompile. You run it changing this file, and then you run it again and again as many times you want to change your lattice size, your lattice spacing, your volume, your physical parameters, etc. Okay, and how we evolve the expansion of the universe? We use the second-order Friedmann equation, the one that dictates the acceleration of the scale factor, and this is sourced by all kinetic terms of the scalar sectors. gradient terms of the scalar sectors, potential term of interaction, and kinetic and gradient terms of the gauge sector. So here are the typical expressions. We don't need to comment them in detail. They are the typical expressions of a scalar dynamics or gauge scalar dynamics. Okay, so for instance, this case here of U1 and SU2 represents electric fields. And this GU1 or GSU2 represents magnetic fields of abelian and non-abelian flavors. And then we use the first Friedman equation as a constraint equation. So we check in our dynamics that they are right, because we need to verify this balance of the left-hand side with the right-hand side at every moment. Where the brackets, remember, of course, for the Friedman-Lemaitre-Robertson-Walker formulation, this represents volume average. Okay, so my distribution of the fields can be very inhomogeneous. As long as I capture that inhomogeneity inside the volume of my box, then you can still solve for the background of the expansion of the universe taking these volume averages, okay? As contributed by all the energy components, all the energy elements, kinetic, gradient, electric and magnetic, and potential of your interactive fields. What kind of outputs you can produce? You can really produce a variety of outputs, from mean values of field amplitudes to energy density components, to spectra of any kind, field amplitudes, occupation number, energy density spectra, whatever, and then three-dimensional distributions like two-dimensional snapshots or the full three-dimensional distribution directly. You can really choose what to plot just by choosing in a menu with a single click. So in summary, Cosmolattice is a very complex and advanced code which overtakes, if you want, the classic lattice that we all use for so many years. The idea is to go a bit advanced than lattice and to make it more powerful, okay? Now, Cosmolattice is a very general code. It's not meant just for the type of theories I told you, but it's more generic. It's really thought for solving any field theory problem you may have, characterized by a set of initial conditions and the characteristic equations of motion of that field problem. So if you learn the language of Cosmolattice to introduce in the code these equations of motion in the lattice language of Cosmolattice, then Cosmolattice is gonna lattice your whole system. And then it's very simple. You just choose what time step you want to choose, what number of points per dimension. This depends on the memory you have in your system, what lattice spacing. Then you choose what algorithm you want to use to solve your system of equations. We have a family of all the typical algorithms, which are both symplectic and non-symplectic. And this has been tested in multiple purposes and contexts, and they work really well. Then you choose your physical parameters. Remember, there is a file, you choose your values. This goes for dimensionless parameters, but also for dimension full, like masses, vacuum expectation values, field amplitudes, etc. And finally, you choose what observables you want to print, press play, and then you get your output, okay? So it's rather simple as long as you learn this first step, which is how to introduce in the language of Cosmolattice your system of equations of motion. So essentially, Cosmolattice is a platform for field theories, and you can choose the problem to solve. You can introduce new problems. Of course, this can be a new problem introduced within this type of dynamics, so scalar field dynamics, abelian gauge dynamics, non-abelian SU2 gauge dynamics, as I was commenting before. But because it is a generic code, we are already working out in including other features and interactions. For instance, in the next year release, we are going to release the capability to compute and simulate gravitational wave production from any source of the fields. So essentially, from any matter sources, no matter scalar or gauge fields, no matter how nonlinear or inhomogeneous, you are going to be able to compute the gravitational wave production. We are also incorporating axial type of interactions of an axion type field to FF dual sector to FF dual operator of a gauge sector. We are also including non-minimal gravitational interactions and the ability to simulate any network of cosmic strings. And as a matter of fact, because gravitational waves are so important nowadays, we've already released the module to do a scalar field gravitational wave production. So essentially, for any system of scalar fields that you want to simulate, you can already compute their gravitational wave production with our module, and it's publicly there. You can download it at any moment. So as you see, Cosmolattice is very versatile, and it has really many applications. You could simulate preheating, equation of state after inflation. You can also simulate gravitational wave production from any kind of nonlinear dynamics, for instance, in preheating, but not only. You can simulate the nonlinear dynamics of inflation. You can simulate cosmic string networks. You can simulate isolated defects. You know, if you just want to study them isolated, non-minimal gravitational interactions, phase transitions, and whatnot, your own project, okay? But time is finite, obviously, so I'm gonna give you a selection of topics. I'm gonna present you a selection of topics. I'm gonna focus mostly in these first two topics. Sorry, give me a second to drink. And so I've prepared this first topic. It's about gravitational waves from nonlinear dynamics, and I'm going to focus in an example of preheating after inflation. Second example is about nonlinear inflation dynamics, and I'm going to focus in axion inflation. And then, if time permits, I would give you a taste in 5 minutes each of how you can simulate the single dynamics of string loops, for instance, or how you can deal with non-minimal gravitational interactions of scalar fields, okay? So I'm gonna start with the first part, which is this topic, but I don't know, is there any question? Because since I don't hear nothing, you know, I have no feedback right now. Is there any question up to here?
One question.
Okay.
Daniel, hi. It's Dima Gorbanov.
Oh, hi, Dima. Hello. Yeah.
Daniel, obviously you checked your code against other on the market. What about H-lattice, for example?
What about which one? Sorry.
H-lattice.
Compared to H-lattice in particular, I haven't checked it. I've just checked, you know, like all the stuff with lattice and my own codes, you know, because for many years I developed my own codes, but I never made them public. However, for your tranquility, just to let you know, because H-lattice, for instance, have some of these higher order integrators. We also have these integrators, but we not only we have them for scalar fields like H-lattice, we also have them for gauge fields. And there is self-consistent tests you can do to check the quality of our integrators. And those self-consistent tests are energy conservation and Gauss law. And I can tell you that our integrators preserve very well energy conservation. We can even go up to machine precision, and we always conserve the Gauss law to machine precision. Okay, so even though I haven't done a test explicit with H-lattice, because at some point I cannot go crazy about testing everything, we have internal checks, you know, and these external checks pass the test. So I'm pretty confident by now that, you know, there can always be typos, of course, you know, Dima, but the algorithms we have released publicly for scalar gauge field dynamics, they work as they should, you know.
Okay, thank you.
Thank you. Thanks for the question.
Another question, Daniel.
Yeah.
What are your typical lattices, and how many Hubble times can you simulate on on achievable resources? Okay.
Yes. So typical lattice depends on your resources. Okay. On my laptop, I do 256 cube. In my local cluster, I do usually, if I need it, of course, because if you don't need to do big simulations, there is no need, but I can reach easily 1,000 cube, 2,000 cube. And then we've tested Cosmolattice scaling well up to 8,000 cube, okay? So this depends on your resources. To do an 8,000 cube simulation, you need a gigantic mega cluster for yourself. So we've done runs in more than 100,000 cores, okay? Mm-hmm. But typically people don't have access to this. So if you have access to a more modest cluster, like say you have you can run in 500 processors or 200 processors. Then you are going to be able to do 1,000 to 2,000 cube simulation.
Say,
Okay,
yes, say for the simulation with 2,000 or 1,000 cube, okay?
Yeah.
How many Hubble times can you realistically simulate?
Yeah, so this, again, now it depends on the problem you want to simulate, okay? So if you are in post-inflationary physics, I think typically, I haven't counted in Hubble times, but in post-inflationary physics, since the scale factor only grows as a power law, a smooth power law, I think you can simulate for very long, for long enough. If you want to simulate inflation, however, the maximum I have reached is 10 e-folding. Okay, I don't know if this answers a little bit your question. So I cannot do more than 10 e-folding in inflation so far. And actually, you will see my second topic, I'm going to show you those simulations. Okay, so at the end of the day, how long you can simulate, it depends. What's the accuracy of your integrator? What's the sensitivity of your physics to boundary conditions? Because sometimes you are sensitive, and once you hit the horizon size of your box, then you are done. You cannot go any further, okay? But in other applications, it doesn't matter, and you can go on and go on, you know? And for instance, for preheating, I did a trick recently with other collaborators. We simulated 2+1 dynamics instead of 3+1. We did a matching between the 2+1 and 3+1, and we saw it works pretty well. And then we simulated up to 15 e-foldings, you know, after end of inflation.
Oh, okay, thanks.
Yeah, that's pretty much a generic answer. But yes, it depends on the problem, but we can do very beautiful things. Let me put it that way. Okay. And you can do it also if you learn how to use it. That's the message of the talk. Okay. Okay. Shall I continue?
Yes.
Okay, excellent. Thank you guys for the question. So, first example is about how to reconstruct particle couplings, so particle interactions with gravitational waves. This is in collaboration with this bunch of people, and I highlight in red my student, Nicolas Loaiza, who is actually doing the implementation in Cosmolattice of this problem, and who is also responsible for the gravitational wave module that I'm going to use here. So what is the motivation I have here? Well, we know that non-perturbative dynamics, like in preheating, but also in strong first-order phase transitions, they create very sizable gravitational wave backgrounds, typically with a spectrum in omega gravitational wave energy density versus frequency with a single peak, or sometimes there is some more complexity here and there can be two peaks and so on, no? But what I want to address here is, what if I have a multi-particle state? So what about if I have many different particle species coupled to the main source of gravitational waves, or they are themselves as sources of gravitational waves? If that's the case, can we reconstruct the particle couplings of their interaction through signatures in the gravitational wave background? This is what I want to address here. And of course, I can only do it in an example. So I'm going to choose a simple model, which is inspired by alpha attractors, which is to choose this kind of potential. For the inflaton, this is a potential that flattens out at the large field values, but then becomes a monomial around zero, so that when you end inflation, the inflaton starts oscillating after the end of inflation. But at the same time, because the potential flattens out at large field values, where you do inflation, you verify all the inflationary constraints. There is no problem with CMB constraints. So now imagine we play the simple game that everybody has always played in preheating. I choose a preheat field, a dotted field, chi, coupled to my inflaton phi. And then we study the dynamics of this preheat field chi in the time-dependent background of the oscillations of the inflaton. And of course, this is well known, you know, because I think many people in the audience know this very well, that you excite through parametric resonance this dotted field for appropriate choices of the coupling, of course, and this amounts to an exponential growth of the amplitude of the fluctuations of this chi field, of the dotted field, within an infrared band. And this is called broad resonance. I'm not going to enter into the details of that because I'm going to focus into something else, but let's say that starting preheating typically amounts to starting oscillator time equations for the mode fluctuations of this kind with a scale and time dependent effective frequencies. In the linear regime, of course, this is relatively easy. You can solve it in Mathematica or sometimes even analytically. But still, this is a non-perturbative and out of equilibrium phenomenon. Okay, so it's a complicated phenomenon of field theory. But it becomes even more complicated once you enter into the mode coupling. Once the system becomes nonlinear and the field modes talk to themselves through the interactions, then the system becomes nonlinear. And then you really have to go to the lattice. So essentially, in many scenarios of preheating, for a specific range of momenta, the amplitude of the field fluctuations or their occupation number becomes macroscopic, and this turns into large inhomogeneities of your field distribution. There is a typical length scale inverse to the typical momenta you excite with a high energy density contrast and relativistic velocities. And this, of course, well, graphically, it looks like this. This is a two-dimensional cut of a given simulation, and I'm plotting the amplitude of this two-dimensional cut of a Higgs-like field, and you see they develop inhomogeneities. Eventually, these inhomogeneities, they collide, they break into smaller inhomogeneities, and the whole system becomes very nonlinear. And this is a typical example of what's going on in preheating. And it's been known for ages, of course, that preheating is a very effective gravitational wave generator because of these nonlinear dynamics, okay? Because of the linear dynamics initially and the nonlinear dynamics afterwards. So, because the system becomes nonlinear, we're gonna simulate it in the lattice, for which I have a beautiful tool now, which is Cosmolaris, and I'm gonna use the module that my two students, Nicolás Loaiza and Jorge Baeza Ballesteros, has already worked out in full detail. Now, let's work out the dependence of the spectrum of these gravitational waves in these simple preheating models, okay? In these preheating models, where there is a monomial potential at around zero, and then the inflaton oscillates, produces through parametric resonance the preheat field excitations. This sources gravitational waves, and this is how the typical spectrum of gravitational waves looks like. This is omega gravitational waves, is this fraction of the logarithmic energy density spectrum to the critical energy density at the time of production versus normalized momentum appropriate for the units of the simulation. And what you see is typically there is a single peak. No, there is a maximum height, and this maximum peak is located in a given position. And both the height of the peak and the location of the peak is essentially controlled by the resonance parameter. The resonance parameter codifies all the physics, the strength of the coupling of the dotted field to the inflaton, the initial amplitude of the inflaton, just when the oscillations start, and the typical frequency of these oscillations, which is nothing else by a measurement of the curvature of the potential of the inflaton at the onset of the oscillations. Okay? And essentially, people have worked out, I worked it out with my first PhD student, what is the parametrization of the amplitude of this spectral background of gravitational waves as a function of the resonance parameter. And to be simplistic, let's say the scale is inversely proportional to the resonance parameter. Whereas the location of the peak actually depends as a weak power law of the same parameter. So essentially, once you know the resonance parameter, the initial resonance parameter, okay, because the real resonance parameter changes with time in the problems, but the initial one determines already where you are going to get essentially the amplitude and position of your gravitational wave background. And it's been known forever, you know, because many people have worked out that this can be very large background gravitational waves, reaching amplitudes today in omega factor of 10 to minus 9. But here, what I want to focus is not how large it is, because I think this has been worked out for many years, is on the fact that, remember, the amplitude of the spectrum actually peaks in inverse of the coupling. And the frequency actually is determined linearly by the coupling, roughly, okay? There are some numeric coefficients here. And this is very interesting because now the question I want to rise up is, what about if I have multiple preheat dotted fields coupled with different strength to my mother field, to the inflaton. And if I do have such a situation, which I think you should expect in preheating, no? To have more realistic scenarios, you would expect naturally to have a multi-particle system. The question is, can I do a spectroscopy of the particle couplings with the gravitational wave signatures? Well, in order to address this question, I'm going to put it in my cosmolary simulations, and we're going to run a bunch of simulations. So if I put a single preheat field, let me call it Chi1, then you already know the answer. You get a single peak with position and height of the gravitational wave spectrum, omega gravitational waves versus frequency, determined by the strength of this, determined by the resonance parameter, which is determined in a given scenario by the strength of the coupling. If I simulate another universe where I have again a single preheat field but with a different coupling strength, now I'm going to get again a single peak spectrum of gravitational waves with amplitude at location determined by the different strength of the second coupling. So the question I want to address here is, what happens if in reality I have the system with the two daughter fields coupled simultaneously to the inflaton? So that each of them is coupled with the previous coupling strength when they were coupled separately. And, well, we've simulated this system, and guess what? Well, you probably are guessing in advance what you are seeing in the screen. The spectrum now inherits the structure of the original single daughter field peaks, such that the amplitude of the peaks is not as high as before, because due to energy conservation, you cannot pump the same amount of energy, but the position of the peaks, it is in the same original location, because this is dictated by the physics of parametric resonance of each species. So essentially, this is what you get. Can I generalize this? Now imagine I do 3 daughter field species coupled to the inflaton, and I'm going to show you an animation by Nico, my student. And essentially, initially, the spectrum of gravitational waves versus appropriate momentum. It's just noise, but then as we go by with the dynamics of preheating, we start seeing that 3 peaks emerge in the spectrum of the energy density of gravitational waves. And you see that here I'm signaling the position of the peaks. These vertical lines are actually the predictions from the simulations of the single preheat fields with those couplings, whereas the red spectrum is the simulation with the 3 daughter fields simultaneously coupled to the inflaton. So it's kind of obvious, you know, what you are getting. You are getting a spectrum in the gravitational wave spectrum of gravitational waves that the location of the peaks is determined by the strength of the interactions of these couplings, okay? And we call this signature a stairway signature. We try to call the paper Stairway to Heaven, but of course the editors of Physical Review didn't let us as usual. I don't know what's the problem, because I think it was a very fun title. But anyways, the signature is still called a stairway, and for obvious reasons, no? Because there is a stairway here of steps. So now the question, let's be like addressing the following question. Can I, suppose I'm capable of measuring one of these spectra, okay? And for you know, simplicity, of course, I'm gonna do it with a 2-peak signal, just with 2 daughter fields. I'm gonna take this scenario I simulated. That's a high energy scale scenario of inflation, which typically produces very high frequency gravitational wave backgrounds. I'm gonna use as a template only the spectra I have, and I'm gonna assume I have a scenario that produces a similar 2-peak signal, because there are 2 degrees of freedom involved here, but at Lisa frequencies, okay? So I'm gonna put my template that I generated with my simulations as a template of a background that I inject in my Lisa simulator. So essentially here in pink, I'm showing the noise of Lisa. Well, that's not the noise, that's the power law sensitivity, sorry, the noise is something else. In red here, I inject my signal of 2 peaks, and in orange, this is the reconstruction we do with our simulator of the Lisa detector. And essentially, as you can see, I'm reconstructing pretty well with Lisa a background that would have the same height and peak structure of the ones I've simulated. So now we do Monte Carlo Markov chains to extract the information from our reconstructed spectra, the position of the peaks. We can reconstruct this position of the peaks to better than 1%. And since I can predict as a function of the coupling, what is the position of the peaks, now I can invert the problem, and knowing the position of the peaks, I can predict from the reconstruction what is the strength of the couplings. And essentially here, you see in the example, we injected these couplings in our scenario with these values, and this is the reconstruction that I did in Lisa in blue. And if I do the reconstruction, for instance, at BBO, assuming I have a signal at Big Bang observatory frequencies, then the reconstruction can be even better, obviously, because BBO has more sensitivity. So in other words, we are demonstrating with this exercise that in the future, if we have signals in the appropriate frequency range, we are going to be able to do particle physics, maybe not as good as in particle accelerators, but we are going to be able to reconstruct coupling interactions, okay? So our example should be only taken as a proof of principle, because the scenario we really simulated in reality is a high frequency scenario. But if you think of other scenarios at lower energy scales, there is no reason to think that there's not going to be similar multi-particle situation. So the game I'm playing right now with my team, with my students and postdocs, is to look for these multi-peak stairway signatures at low-scale preheating scenarios and phase transitions. Of course, one should never forget that there's the possibility of measuring high-frequency gravitational waves, maybe in a long future, and hence you could really access to the kind of scenarios of preheating. But so far, the plethora of gravitational wave detectors that have been planned for the next 2 decades are rather on low frequencies. So the idea is to play this game of looking for multi-peak stairway signatures in low-scale preheating and phase transitions at the scales in which you generate observable signals. With this, I have concluded the first part. Maybe before I go into the second part, are there questions here?
No, at the moment, no.
Okay, then I will carry on. Okay, second part, maybe even more interesting for people in the audience, is about how to simulate the nonlinear field dynamics of inflation, and in particular, because depends on your scenario of inflation, nonlinearities means one thing or something else. I'm going to focus on action inflation because I think it has a very clear interest from point of view of particle physics. This is in collaboration with my Basque group of colleagues, and I highlight here in red Ander Urio because he is the PhD student who is actually doing all the hard work of first implementing this in the code and secondly running the simulations. Okay, so within the family of inflationary scenarios, which we know there are hundreds of them, I think when you have a taste in particle physics, we like the idea of action inflation, which is to invoke a shift symmetry, such that the inflaton has this symmetry. It can be shifted by a constant value. And this is very interesting because it allows to couple it in a derivative manner to either fermions or gauge fields. And one of the most interesting couplings is when you couple this shift symmetric inflaton to FF dual of a gauge sector. Okay. Now, of course, in order to do inflation, you need to invoke to some non-perturbative effects, which here are unspecified, that give a potential to the inflaton so that you can do inflation. This is maybe a weak point of these scenarios. The strong point is that once you assume this kind of interaction, due to the shift symmetry, the phenomenology is extremely rich. Okay, so I'm just going to follow now what is this phenomenology. Essentially, I'm going to focus for simplicity in an abelian gauge sector. So essentially, you can think of your gauge field as a photon-like field. Of course, not necessarily any of the gauge fields of the standard model, just a photon, a dark photon, if you want. It could also be, of course, the hypercharged gauge field of the standard model, but then it would require other ingredients. So let me not enter there. So in a dark photon scenario, essentially, if you study the two helicities of this gauge field, then you immediately realize in the equations of motion that this is a chiral coupling that differentiates the two polarizations, because the sign in the effective frequency is different for the two polarizations, and essentially one of the modes is going to be tachyonic. The whole effect is controlled by this psi parameter, which is a manner of measuring the velocity of the inflaton normalized to the decaying constant of the action and to the Hubble rate, okay, by just the velocity, if you want. And this is a chiral instability because since one of the modes is tachyonic, it's going to grow exponentially fast, whereas the other one is going to remain in vacuum. And this is well known. People have worked out this for more than over 10 years. And since there is this chiral instability in the tachyonic polarization of the gauge field, I choose here A+. Well, there is a huge phenomenology associated, because then it means immediately that if you excite the gauge field like this, you are also going to excite through inverse decay the inflaton perturbations, and you're going to produce very large inflaton perturbations, actually highly non-Gaussian. And this is very interesting, this non-Gaussianity, because you can use it to put constraints from CMB due to the lack of observation of non-Gaussianities into the coupling strength of phi to FF dual. Also, the amplitude you produce of these scalar fluctuations at short scales, so not CMB scales, but way later in inflation, after the 60, after the CMB modes cross the Hubble radius, way later, you can continue producing fluctuations, and you must bound these fluctuations to prevent that you produce too many primordial black holes. So you can again use this to put constraints. And then finally, because you excite so much these gauge fields, they can act as a source of gravitational waves, and they are going to produce beautifully a lot of gravitational waves. And actually, this is going to be a chiral background because the source is chiral gauge fields. So I'm going to focus on the gravitational wave production. Here is an example in a scenario where you have IFF dual, and here is the spectrum of omega gravitational waves versus frequency that you produce. And you see it's very blue tilt because it's growing with frequency and is way above the standard vacuum quantum fluctuation spectrum. It's blue tilt, it's chiral, and it's non-Gaussian. And then it's very interesting to ask the question, can we really detect this background of gravitational waves and hence measure properties of axion inflation? And the answer to that question depends, of course, very sensitively on the details of the excitation of the gauge fields. The excitation is exponential on the velocity, so essentially you need to capture that very well, which means the spectrum of gravitational waves is extremely sensitive to the choice of potential and to the details of your calculation. And here is the problem, that all the primordial non-Gaussianity, gravitational wave production, and primordial black hole constraints have been derived using a set of approximations, analytical or going beyond analytical, but always approximations. And it turns out this is not exactly correct. So let's have a look to the full problem here at hand and understand why those approximations are actually not so good as people think. In order to understand this, let me define variables. Let me call pi my velocity of the inflaton, electric field E, magnetic field B. Then with tilde, I make some conformal redefinitions of pi and electric field, and I call the first derivative of the scale factor pi A. Now, if I write now the dynamics of the matter fields, I have here the local equations of motion, and I emphasize local because these are a function of space, of the point, not only of time. And here is the first equation, is the dynamics of the inflaton sector as sourced by the EB term that comes from the FF dual. And second equation is the dynamics of the gauge field, which is in interaction with the scalar sector through pi here and through this curl here with the gradient of phi. And at the same time, we have to solve for the dynamics of the expanding background, which means to solve the second Friedman equation, which is this, which is sourced by the volume average of the kinetic and potential energy of the inflaton and the electric and gradient energies, or electric and magnetic energy of the gauge sector. Okay, I have to take all these three set of differential equations which are coupled with each other and solve them at the same time. The system is going to be nonlinear because the equations are coupled among each other. But of course, people, in order to do some analytic progress, more than 10 years ago, they first solved the linear regime. So they eliminated any feeling of inhomogeneities. Okay, they removed the Laplacian of the inflaton, the gradient curl with electric field, and they removed the source for the inflaton and just consider the interaction of the inflaton, the velocity pi, with the magnetic field here, which is the same as the tachyonic instability I was discussing before. To be consistent with linear regime, of course, you also eliminate back reaction into the expansion of the universe, so you remove even the back reaction of electric and magnetic fields. But of course, we know that this is not good enough because there's going to be eventually a back reaction if you have a tachyonic instability. Because if you are pumping so much energy into the gauge fields, it means that the electromagnetic energy density is going to be sizable, and first is going to back react in the expansion of the universe, and second is going to back react into the dynamics of the inflaton. So people realized, of course, in 2013 that you needed to do back reaction, but the only easy way to do it that people have been working out so far is to do the homogeneous approximation to back reaction. In the case of the back reaction of the scale factor, this is correct because it is the homogeneous expectation value, if you want, of the electromagnetic energy density that contributes to the expanding background. But in the case of the scale factor, this is just an approximation to take the expectation value of E dot B. Now, this expectation value, of course, can be expressed in terms of the spectrum of your gauge field mode functions, okay, on the spectrum of the gauge fields. And so people turn this linear equation of the gauge field into an equation of the mode functions of the gauge field. They solve for their tachyonic instability. And the problem, since this is a coupled system, every time step you solve for the tachyonic instability, you have to plug it in the expressions here to compute the expectation value of EB and electromagnetic energy density, then above the inflaton, then again one step of the gauge fields, then one step of the inflaton, and so on and so forth. So people work out an very elaborated iterative system that works, but is extremely inefficient and slow. However, another set of people already last year, they work out the same system, homogeneous back reaction, but with a much more elaborated approach, which is the so-called correlator gradient expansion. I'm not going to enter into the details of that, but essentially they take correlators they take expectation value in the whole system of equations, and they rederive a new family of equations for the expectation values. And they can solve, the previous papers would take 1 day to solve one simulation. Now these people can take seconds to solve the whole system of homogeneous back reaction, which is good. But the question I want to address here, and I'm presenting to you, is can we do better than homogeneous back reaction? And the answer is, of course, yes, as long as you know how to introduce in the lattice this operator. Okay, this operator is complicated, but if you know how to put in the lattice, then you can deal with the full inhomogeneous back reaction. And if you want to do that, which I do, then of course I restore my equation of motion in terms of my original field variables, and I need to restore also the information in the inhomogeneities, because now I'm going to simulate the whole inhomogeneous system in a lattice. No? And to conserve energy and Gauss law, of course, I need the full balance of all the terms. So let me lattice this system of equations of motion. It turns out that I had already done the job with Misha, with Misha Shaposnikov, when I was working with him in another problem a few years back. In another problem that required an action, so we latticized this problem, and then I generalize it for expanding backgrounds for this context with another student.
Excuse me, can I ask a question?
Yes, please.
The question is, so this tachyonic instability, it happens on the preheating stage?
No, I'm talking about inflation.
So during inflation, you have tachyonic instability of one chirality of the...
That's correct. That's correct. Yeah.
So does this lead to huge non-Gaussianity, no?
Yes, it does produce huge non-Gaussianities, but as you are going to see in a moment, we are mostly interested in the last stages of fraction inflation when the system becomes nonlinear, and in those stages the scales are small enough that the non-Gaussianities are at a smaller scale, and I don't care from the CMB point of view. Okay, so from the CMB point of view, where I put strong constraints in the non-Gaussianity, for the couplings of choice I take, they respect the CMB non-Gaussian constraints. Okay, so
what is the parameter which you tune to suppress the non-Gaussianities?
This coupling lambda here.
So we have just small coupling, so small tachyonic instability.
Exactly. I prevent tachyonic instability from happening in an efficient manner at the CMB scales. So I let inflation continue until the tachyonic instability builds up in such a way that the system becomes nonlinear. But this happens towards the very end of inflation when the scales are much shorter than those characteristics of CMB scales. Hence,
yeah. So you tune the scale to be in the very end of inflation.
I tune the scale, but the only thing I'm choosing is the coupling. Once you choose the coupling, what is the scale at which you would produce sizable excitation is fixed due to the dynamics.
Okay, thanks.
For a choice of potential, of course. Yeah. Okay, thank you. That's a very good question. I think it's going to become more clear now when I show spectra. So, okay, I don't want to bore you with technical details on the lattice. I just want to tell you that this is how to lattice the system. Misha and I, we introduce a combination of plaquettes of electric fields, 2 plaquettes for electric fields, 4 plaquettes for magnetic fields. There are technical reasons why one has to choose this. Okay, I'm not going to enter into that. Just want to highlight that our formulation is gauge invariant at the lattice level. It reproduces the continuum limit to second order in lattice spacing. It respects exactly the Bianchi identities in the lattice. And the most important thing, it respects the topological nature of the operator FF dual. Because the reason why phi FF dual is a derivative interaction compatible with the shift symmetry is because FF dual, of course, is a total derivative of the Chen-Simons current. But any formulation that people have done before, they are always breaking that in the lattice. However, Misha and I, we found a formulation that for a billion case, it is possible to have exact total derivative of a Chen-Simons current. Hence, we respect exactly the shift symmetry on the lattice. Okay, and this is the importance of our formulation. And all maybe you need to know about this at this level. So just for you to understand a little bit this system of discrete equations I put here on the top box, if you look at the bottom box, what you see is the continuum equations, and now I match the terms that I represent by the lattice here. So you see this bilinear combination of plaquettes of electric fields times a semi-sum of 4 plaquettes of magnetic fields represents this source term. This other term with semi-sum of this kind represents the interaction that gives rise to the tachyonic of the chiral instability. And finally, this more complicated term reproduces the gradient of phi curl times E. Okay? Good. So we have this system of equations of motion in the lattice. Now we have to solve simultaneously the expansion of the universe, say the second derivative of the scale factor, as sourced by the energy and pressure, or energy density and pressure of all the matter fields in the game. So kinetic energy of the scalar inflaton sector, gradient energy of the inflaton, potential energy of the inflaton. Here I'm choosing a quadratic guy, okay, for simplicity. electric energy density, magnetic energy density. Here are the expressions, are the standard expressions. Here are just the lattice discretized expressions, okay? So we are gonna solve in the lattice simultaneously this system of equations during inflation, okay? And what I'm gonna show you is not published yet, is work in progress, but we are really about to make public this, if not in December, in January next year. So for simplicity, I'm gonna compare to a quadratic potential because this is what the community of people working in this model have been doing so far. But in reality, we could do it for any potential, even one compatible with shift symmetry, obviously. So what we are gonna choose is a value of this lambda here, using this vertex, this phi FF dual with this 4 here. I'm gonna choose lambda equal to reduced Planck mass over 20. Now, if I was ignoring the gauge field production and the whole system of inflation was determined by the scalar field sector, this is what would happen with the epsilon parameter. Towards the end of inflation, here I'm counting number of e-folding backwards till the end of inflation, which I labeled as 0, the epsilon parameter would grow until it hits 1 and you end inflation. In reality, we know that at some moment, you are gonna generate, in this moment is minus 2.7 e-folding in this scenario, you are gonna generate so many gauge fields that they have so much energy that they are gonna back react. And the real epsilon parameter in my system is this blue line, okay? This is the really nonlinear regime of inflation. So essentially what you see is that we are extending inflation. We are gaining 4 extra e-folds of inflation for this particular choice of coupling, of course, and the epsilon parameter goes up, stops the growth, so you don't finish inflation by breaking a slow roll, but you actually start back reacting from the gauge field. The epsilon parameter goes up and down, and finally goes up due to gauge field domination. Okay, so it's actually the gauge fields that are gonna end inflation. What's going on? And this has to do with the question you guys were asking me. So I'm gonna count e-foldings using numbers as if we were in linear regime, okay, from minus 6 e-folds to 0 e-folds. So at minus 6 e-folds, in these scales I'm simulating, which are around the mass, okay, which are scales, the peak of the scale follow the horizon. So just to give you an idea, the co-moving horizon, sorry. I'm starting with Banks-Davis vacuum, and then as I go with the tachyonic instability and the foldings go up to 0, okay, then you see the tachyonic instability of the gauge field here. It grows orders of magnitude, the amplitude of the gauge field spectrum versus momentum. However, since the system at some moment turns nonlinear, now I'm showing you the real spectra from our nonlinear simulations, and you see the amplitude of the gauge field at the would-be 0 folding according to the linear regime is way lower than before, okay? So the would-be end of linear inflation, I have a different gauge field excitation. Because there was back reaction before. But however, we know, because I showed you before the epsilon parameter, that inflation continues now, which means there's gonna be a bunch of other few foldings, and then my gauge fields continues being excited. And because this excitation is exponential, just imagine you are pumping more and more energy into the gauge field until it fully dominates the system of matter fields. So essentially, the end of inflation is going to be the end of nonlinear inflation with extra folding compared to linear physics due to the gauge field domination. Furthermore, if this is the tachyonic polarization that was excited during inflation, if I plot the total gauge field spectrum, now in dash, now what you see is that it doesn't overlap exactly with the chiral polarization. And why is that? Because it turns out that the other polarization that according to the linear regime or homogeneous approach, you thought it would never be excited because you never see that excitation in the equations of motion. Once you introduce inhomogeneities, it turns out that you excite the longitudinal component of the gauge field, and this also excites the other non-tachyonic polarization, which is now in dotted fields. Which means the real prediction of this scenario is to reduce the imbalance between chiral difference between the polarizations. So this is a zoom of the same power spectra. In dash is the total gauge field. In continuum is the tachyonic polarization. In dot is the polarization you thought it wouldn't be excited. It's not excited as much as the others, but it is excited in the UV modes almost equally, and also in the infrared. Okay, so it turns out that taking the whole inhomogeneity is crucial to understand the system, because not only it's crucial to understand how many extra foldings you have, it's also crucial to understand what are all the degrees of freedom excited. And another way to picture all of this is to look at the energy densities, different components, here in red kinetic inflaton energy density, in green potential, and in blue electromagnetic gauge field energy density. In the linear regime, you are just pumping energy to the electric and magnetic fields, and since they don't back react in the linear regime, they just grow above the source, which doesn't make sense, because in the nonlinear regime, we need to conserve energy, obviously, which means that once you pump sufficient energy into the electromagnetic system, you dump the kinetic energy of the inflaton, and instead of finishing inflation by the breaking of a slow roll of the inflaton, in reality, you dump the kinetic energy, you are dominated with the gauge fields over the kinetic energy, and eventually the gauge fields reach the potential energy and you end inflation, which is what determines this last extra folding, okay, with gauge field domination. So how relevant is all of this? Well, here is the here is the money plot, okay? If I plot the psi parameter, which is a way to measure, remember, the velocity of the inflaton, and that's what controls the gauge field instability. If we follow the linear physics, this would just grow like that until the end of linear inflation. But in reality, we know there is non-linearity, so the psi parameter stops growing, actually goes down, bounces back, kind of wiggles a little bit, and then goes down in the extra folding of inflation we are getting. And of course, it turns out that the homogeneous back reaction, they also capture that. Okay, they also capture that effect. However, look that the number of foldings they get is not the correct one, because they are not capturing the inhomogeneity locally, the local inhomogeneity. And also, the size of psi for them oscillates much more abrupt than what in reality we see. And this has very important consequences, as I will comment in a final transparency. So just to conclude, imagine I change the coupling now by 25%. So I reduce this lambda, which means I enhance this lambda, which means I make weaker my coupling of phi to FF dual. Now, in cosmolattice, we can also simulate the homogeneous back reaction. Nothing prevents us from taking expectation values in the sources and removing gradients. We can do that. And this is the epsilon parameter in our own homogeneous back reaction simulations. For this weaker coupling, what you see is that you get also extra foldings of inflation compared to linear physics. But if I compare to the inhomogeneous case, now the number of extra foldings I get until the end of inflation is smaller than in the homogeneous case. Whereas in the previous coupling, I was getting more extra folding in the inhomogeneous situation compared to the homogeneous back reaction. So essentially, the amount of extra foldings you get compared to homogeneous back reaction, it's non-monotonic with the coupling, essentially. This is what we are showing. We can compare, of course, our control of homogeneous back reaction. This is the psi parameter again versus number of folding. And I'm showing in yellow our homogeneous lattice simulation, and in green what people do in green gradient expansion. And you see here, it even turns negative. It flips sign. This is why there are dots here, because the velocity is flipping sign in the homogeneous approximation. But in reality, once we switch back the full inhomogeneity, there is no such a flip of sign. Okay, and you see these oscillations disappear in the psi parameter, and well, you see there is extra different behavior, and the extra number of foldings is just different. So why is all of this important? Because this psi field controls the gauge field excitation in an exponential manner. Any linear change in psi has an exponential response in the gauge field excitation, which means that all the predictions and constraints in primordial non-Gaussianity, but especially in primordial black holes and gravitational wave production at small scales, depend crucially on psi. And psi has not been correctly computed in any other previous computation until we've been able to include this in homogeneities. So essentially now we have the technology to reassess all the real observability of this system, which includes PVH constraints, gravitational waves, and so on and so forth. We also have the power, of course, to add Swinger pair production through effective current like this, and we can study other phenomena as baryogenesis, magnetogenesis, which are very interesting in this scenario. And all of this will be soon in the archives. Well, just if you are interested, I think we will put it, if not in December, in January, I hope, okay? And now, please, guys, tell me if I should stop here. I can stop here and go to the conclusions, or if I have extra 10 minutes, I can give you more taste of this. You tell me.
Then you can continue, I think.
Yeah. Okay, let's say I have example 3 and example 4. I do example 3 in 5 minutes. And again, I ask you the question if you want me to finish or not. If not, we go to example 4. If not, we jump to conclusions, okay? Okay, example 3. I'm gonna try to be faster now, okay? This is gonna be 5 minutes. Here I'm gonna show you how to simulate a single loop from a whole network of cosmic loops, of cosmic strings, sorry. And these are simulations with my student Jorge Baeza Ballesteros, the name of which is already familiar to you because he's also the guy who did the gravitational wave module. We are gonna study the dynamics of a single loop and its gravitational wave emission. So the goal is this, dynamics of an isolated loop from a network and the real gravitational wave emission of a loop. And take into account that this is the first time that anybody is really computing in full general relativity at perturbative level, but I don't need anymore, what is really the emission of gravitational wave of a loop. Because what everybody is using in order to do computations is Nambu-Goto approximations that people work out, Vilenkin and others many years ago. Okay, so how do we get our loops, our loop configuration? We can do semi-analytical techniques. We use Nielsen-Olesen vertexes. We put straight segments. We cross them with velocity, and then we will get a loop inside. Or we simulate a phase transition with topology in the vacuum manifold that will get rise to a network of cosmic strings, okay? We can do either way. In the first way, in the semi-analytical approach, we make these segments to cross with velocity, and they naturally chop off an inner loop and outer loop, okay? They are periodic boundary conditions, so I have two loops. Then we cut the inner loop, which is complicated. If you want to ask me later on after the seminar, this is not easy to do because of periodic boundary conditions, but we can do it, okay? Or in the second case, we simulate phase transition, we produce strings, we let them evolve for a while, and in some situations, we manage to get a single loop in a region of space. So we cut this region, and then we simulate this single loop, okay? Now, preliminary results. First of all, we can measure the decay time of these loops. And of course, the decay time depends on the length of the loop, on the invariant length of the loop from their system of reference. Essentially, they more or less fulfill a linear relation. The coefficient changes depending if this is from the semi-analytical, which we call artificial here, or the network simulating the phase transition. But essentially, there is a linear relationship that tells you the longer your loop is, the longer it's going to live. But the time scale of this life is much, much, much shorter than the life time scale predicted by Nambu-Goto through gravitational radiation. Okay. But during the short time they live, we can now extract the prediction of what is really the energy density spectrum of gravitational waves. What is the spectrum of gravitational wave emitted? And the first result we have, this is for case 1, where we use the semi-analytical approach for the loop, is that in order to measure, this is the spectrum of gravitational waves versus appropriate momentum, in order to capture well this spectrum in the UV, so around the scale of the width of the loop, you need to resolve very well the cross-section of the loop. Because otherwise you produce an artifact emission of gravitational waves, which is not real. So essentially, we had to do studies. They range from lattice of 500 to 2000 cube here, where we are successively resolving better and better the core of the string loop. In the purple, we even gain, I think, more than 500 points in the transverse section of the core of our string. And then you see that this peak was an artifact, okay? And this shows that any simulation that people have done of the whole network with gravitational waves, that some groups have done it, they are capturing this kind of peaks that contribute in a fake manner to the physics. For the second case, where you do phase transition and we isolate a final loop, we see the same effect as we improve the lattice spacing. So we make it smaller and smaller and hence get better resolution. Then we see that this is an artifact, you know, and the peak amplitude at the UV disappears, and the only real emission is here in the infrared part of the spectrum. So here is a measurement of the power emission. This is the typical variable that people use to quantify Nambu-Goto emission. So here is the derivative of time of the energy emitted, the power, okay? I scale out the BEF because I'm not given a given value. You should plug in a physical vacuum expectation value of the phase transition in order to get these numbers, if you want physical units. But I can compare with Nambu-Goto, where I also scale out the BEF. And you see Nambu-Goto predicts that there is a constant line, whereas here we have a very oscillatory wiggle line that even disappears in some cases for the artificial loops and for the network loops. Okay, and this depends on the characteristics of the spectrum, essentially of the how well we capture the dynamics of the loop. So how well our resolution of the lattice is. And well, the prediction is not that bad of Nambu-Goto. It's a factor 5 or so, but the main difference is that the strings are going to decay very fast in this short time scale, 120, 50 units for the given length of this simulation in this example. Whereas Nambu-Goto would predict that they would oscillate many times, emitting gravitational waves with this constant power all the time. And this doesn't happen. We don't see that, okay? The impact of our study, I think, is going to be important for a reevaluation of what is the real gravitational wave emission of loops. And this is going to imply what is the reevaluation of the gravitational wave signal from a whole network in pulsar time arrays. Implications for this are going to be very relevant from dark matter action string networks, because this can be done for global strings, as I was showing you. But I can also do it for local abelian Higgs type string networks. And I can try to solve the problem between, there is a discrepancy in the literature between Nambu-Goto and field theory, because the field theory, the loops decay. Now we can do ultra high resolution of these loops and see if the lattice really has a problem or not. And then this can have implications for grand unified theories, obviously, okay? And again, we are working on this with Professor Copeland from Nottingham and my student Jorge and Joanes Lizarraga from Bilbao, and soon in the archive, hopefully. Now, same question. I have a final topic. If you want, I can skip it and we go to conclusions. If you want, I can cover it again in 5 minutes. You tell me.
Question. There is question.
Question.
Can I ask a question? When you prepare an artificial loop with 4 angles, right? So you kind of have 4 cusps on this.
Yes, on this one, yeah.
So is there an intuition that very high frequency gravitational waves should be coming from these cusps?
Well, if you know the theory from Nambu-Goto, when you have a cusp in Nambu-Goto, it tells you that you have a concentration of emission of gravitational waves around that cusp. Okay, that's what Nambu-Goto predicts. Now, when we have these cusps in this kind of a square type of loops, we thought initially that this kind of emission, this peak, was really related to the cusp. But then when we started resolving better and better the actual resolution of the core of the string, we still have the cusp, okay? But what we saw is that the emission is no more significant than the global motion of the string itself, which is what dominates this infrared emission here. So the conclusion, according to this study, is that if you have a string of this kind, even if you have sharp features like a cusp, like this, the emission due to the global oscillation of the string dominates over the local emission of the cusp. And this is what this spectra of ultra high resolution shows. Take into account that if I'm resolving the
maybe you cannot resolve high enough K to see the gravitational waves from the cusp.
Well, this scale around the width of the core of the string, okay?
Mm-hmm.
And in this resolution with this dx, if I have 0.09, it really means that I have like of the order of 25 points inside the diameter, which means you have of the order of 500-ish points in the cross section. Okay, that is a super high resolution. That is a very good resolution. So what we see here is that when you start moving sufficiently good, your core includes any kind of resolution of the cusp, doesn't look to capture any effect like that. If you tell me you believe that maybe if we still improve the resolution, there's gonna appear here an extra peak due to the cusp, of course I cannot deny that, you know, but it doesn't look like in this picture, because look at the hierarchy of amplitude. Mm-hmm. This is the spectrum in the infrared, and in these units I'm in order 1, and here at the scales of momentum of the inside the core, I'm 3 orders of magnitude suppressed already, you know.
I understood that you don't see any gravitational waves from the cusp. That might be
not dominant. So I cannot rule out the possibility that you could have, but I can tell you that in this study where we changed 6 times the lattice spacing, the dynamics of the string was always the same, but the gravitational waves was affected in this way. Yeah.
Mm-hmm. And the second question is how much longer does it take to compute gravitational waves as compared to the code which doesn't just do the same but doesn't compute the gravitational.
Okay, let me give you an example of the cosmic strings here. Here, I'm simulating a complex scalar field, which is what produces the global strings here. So these are 2 scalar degrees of freedom, okay? If I want to simulate the gravitational waves, I need, in my equations of motion, I put 6 extra degrees of freedom. Of course, this is not because gravitational waves have 6 extra degrees of freedom. It is because it's more convenient to simulate 6 extra degrees of freedom where I don't filter the transverse traceless degrees of freedom, which are the real gravitational waves. And then every time I want to compute a spectrum of gravitational waves, then I can filter those degrees of freedom and make the spectrum. So short answer is I'm going to add 6 extra degrees of freedom. If I had 2 before, it means it's going to take 4 times longer in this case with gravitational waves. Yeah.
Okay, thank you.
Yeah, thank you. Thank you for the questions. More questions?
No. You can continue now.
Okay, if you want, I think I can finish because I don't want to make it infinitely long here, your discussion. And if there are more questions, maybe we can take them here. So let me say that I really thank you very much for the invitation in these difficult times, guys. I appreciate, of course, I think we go to times of peace, I hope as soon as possible. And of course, I would love if that comes to go visit you guys in person, you know, as things should be, okay? Thank you for your attention. I think I've been 1 hour and a half already. Now, of course, if you have more questions, I'm very happy to address them. Or if somebody is curious about the non-minimal gravitational interaction, I'm also happy to cover it. But let's say we finish the seminar here, and then we go to questions.
Okay, thank you very much, Daniel.
Thank you, guys.
More questions? Maybe some questions from the audience online. Well, there are no much people here, but well, I don't see any questions. So thank you again, Daniel.
Okay. Thank you very much.
So,
Thank you, Daniel.
Thanks a lot, guys. Thanks for the invitation, and all you take care. All the best. I switch off here.
thank you.
Thank you. I'm trying to find where to switch off here.
You're trying to exit.
Yeah, I'm trying to exit, but I don't see. I don't see where to exit. Okay. Share screen. Share screen. This is to stop, right? I really don't see where to stop sharing the screen. Okay. I think I see the hang button here, so I'm gonna leave the meeting now. Once again, thanks a lot. Okay.
Thank you very much.
Take care, guys. Take care. Bye.